So this is our 5th year of being here as ATC, and it's governed by a board, a not-for-profit organization called the ATCI International, for which a number of us are board members. We'd like to welcome this year. We welcomed a couple of new faces this year. Kim Wilkerson joined us earlier in the year as one board member, and fresh off the boat yesterday, Joshua Christian joined us yesterday as a board member, so we'll welcome them to our team. It's a group of volunteers. Some of us are retired from our previous jobs, some of us are still working our previous jobs. But there are plenty of us that spend a lot of time doing this job, and we're very happy to have them. In the local area, we have this thing called the HATC, and we would welcome anybody, particularly end users in the Houston area, that wants to join that or be a part of that. We're steadily growing that and changing it a little bit, but it's an adjunct portion of this show, of this event, and we would welcome that growth from the grassroots in the local area. That's run by a gentleman at Shell and our Grant Merriman on the board, so they're heavily active in changing that, so watch this space for the HATC portion of that too. It's all volunteers, and we welcome anyone who wants to come and help out and do a little bit of work with us. This is your volunteers for the conference, and I like to put them up here. Thank you. I like to put them up here because it shows you the number of people it takes to put on an event like this. We will give you the numbers as the week goes on, but we always tell you we're getting bigger and better, and it seems currently that is true every year that we're here. We have more people in the vendors hall. We have a full slate of papers with some spares in the background that we needed, and we think we're going to be about topping over 900 people attending this week. So that will be a record for us, so we're very, very happy about that. So there are a number of people here specifically that do an incredible job for us. But I'd like to thank everybody that's on that board for you in front of you. But I want to pay particular shout out here to Buck Vu's team that does the paper review for us. It's an enormous amount of work. Yeah, please. It's an enormous amount of work for the people to write a paper. And we're very grateful for everybody that's here that's brought their technical papers to us. We are quite demanding in what we expect of our papers. It's a full, proper scientific paper, and then we ask them to come here and present it to us during the week. There's an awful lot of work for each of the individuals that does that. But behind that is a group of people that monitors and moderates and marks those papers for us. And it really is a yeoman task. It really is a lot of work for them. And we're very, very grateful for the people that step forward as part of Buck Vu's team. And I have them listed here for the ones that did it this year for us. We were always looking for more. So anyone that's heading towards retirement has a little bit of time on their hands and wants to read a bunch of technical papers, my great friend, Dr. Bob Baer, should you ever be interested in coming and joining the team, we welcome you with open arms. But anyone that would like to read technical papers through this period of the year, Buck Vu here would be enormously happy to hear from you. So, and thanks to all the rest of the team, of course, on this list. This is your full roster of everybody that puts on this event. I just want to make a quick mention of a couple of people that we sadly lost this year that were very much an institutional part of the analytical community. Our industry is obviously not getting any younger, and we have a number of people that retire every year that we lose, but we hopefully see them come back, which we're very happy for. We have a lot of people that we sadly say goodbye one year and then they come back in a consultancy role next year, which is wonderful. Occasionally we lose some friends of ours permanently. And in this case, there is a couple of people I just want to draw special attention to this year. They were in our newsletter in a much more greater detail for who they were. But I just wanted to make a special mention to two folks. Dan Podkolsky was part of the board of directors here. He spent a lot of time at Exxon, but he specifically spent a lot of time as part of the ISA and the analysis division and the Houston chapter, and then was very instrumental in helping us get ATC up and going, and we sadly lost that gentleman this year. It was a great loss for the team. I think that's fair to say, Wes. The other gentleman I want to mention didn't always attend this show, but anyone that worked in the gas chromatograph industry, and certainly anyone that worked for Applied Automation, Siemens, Valmet over the years would know Rob Dahlgren. Rob did 42 years in analyzers. We don't see that so much anymore, as people tend to move around their jobs a little bit, but there are still a number of people that do that kind of length of service at one company, and Rob was one of those guys. And if you ever dealt with him, he was a fabulous gentleman, and he was an incredible GC chemist. And I think it was just worth a mention that we sadly lost Rob this year. I would also add at this stage, if anybody has anybody within the community that they would like to honor in this way, be it in our newsletters or up here on the stage, we always welcome that. So we're always looking for information and ideas on people we want to honor. So if anyone has a name of somebody that they would like to bring forward, always bring those to us. We'd be happy to share their information with you. Okay. Moving on. What is our conference? For those of you who've been here many times, of course, you know how it works. But for anyone that's new here, I'd like to point out one or two things for you. Yesterday was a training day, and we've spent a lot of time building and building and building upon that training day, particularly since we moved it away from Sunday to Monday. And you'll be happy to know, I think, that we had over 170 people coming for training yesterday. It was a fabulous turnout. It was absolutely incredible. So we're very happy for everyone that came for that, and we're very happy for all those volunteer trainers that came and did that work with us. But we have now two split fundamental courses where we teach the fundamentals of our industry and the technologies that we use. And we have now 3 advanced courses, and all those folks are listed there. And I just want to thank all of those names on the list that came and did that work for us yesterday. That's fantastic. As of today, till Thursday, we now have the papers that will be in here, and you can follow along with those. And in between all of that, you now have the vendors hall for breakouts, for lunch, for the afternoon, and then for the little drink sessions in the evening. And they are usually sponsored by somebody. Follow the board, thank the people that put their sponsorships down. That'd be great. There is a spouses program, I'll mention that in a minute, that is run out of the hotel next door by some very, very thankful spouses that look after that for us.
Our bosses.
There you go. By the bosses, the true bosses. So we're very thankful for them. If anybody needs information, if they haven't already seen it, please let us know. We'll certainly help you out with that. We have a technical paper award that will run through this program, and I'll mention that in a minute. And we have a secret product of the year award, and we'll mention that in a minute too. On the Friday, for those people, most people, the vendors hall always closes by Thursday afternoon, and most people tend to go home unless you're staying for some of the hands-on training with these. These are our vendors this year for hands-on training. So big shout out to them. It's not closed off yet, so should anybody, any end users that want to come in and do work with any of these folks on the hands-on side, please let us know at the front desk or speak directly to any one of these companies. They'll be putting on hands-on technical and service training on Friday. The vendors hall this year has adjusted a little bit. You'll recognize it. For those of you who've been here before, you'll recognize it. But roughly speaking, we're trying to make it a little bit more ergonomically convenient for people to get around and to not be that booth stuck in the corner. We're doing our very best for all the vendors to do that. It's a little bit bigger this year, so hopefully everybody appreciates that. And we've got 117 booth spaces, about 97, 98 individual vendors. So again, another record for us. So hopefully there's plenty of friends and faces that you'll recognize in there, plenty of space to talk and see new technologies and that sort of thing. We've instituted over the last couple of years a program of trying to invite both students to this event, because we're trying to bring in this younger generation to what we do, and some VIP space for key customers, alumni, retirees, a number of things. So today will be a busy day, we expect, with a lot of those VIPs coming through. So it should be a fabulous event out there today. There is a prize, of course, for the paper. All papers received are wonderfully received by this place, and we thank everyone for them. But they do get marked, both prior to the event by the folks that do the reviews of them, and then during the event as the individuals watch it. So we would encourage everybody that looks at these papers, that sits in and sees them being presented, to fill out those sheets, hand them at the table at the back, or keep them with you and hand them in on each day. I think we do it day by day, right, Wes? So for every day, we'd like you to fill it in for the ones that you see, and then hand them to Paul or Josh at the back, and then that way we can tally up all the marks by Thursday. So we encourage that. There's a first and a second, third prize. We have a secret committee run by a secret fellow of ours on the board. Well, the fellow that runs it is not potentially so secret, but he has a secret committee of end users that will be going around the vendors hall this week, looking at those folks that have put their name in the hat to be a product of the year. I think we have a lot this year. 17, I think, potentially. So that's fantastic. So we got lots to look at. There's lots of new things out there to look at, which is wonderful. And it's technically not too late if anybody wants to go forward to the front and throw their name in the hat, but you need to do it quickly. It's definitely too late. It's too late. Hopefully there aren't any new ones. Some of us are softer than other people in this committee board. Some of us are not quite as hardline as the others. It's too late, apparently, but hopefully.
Just mentioned in the future, it's online, and we try to cut it off a couple of days because the judging has already started.
Okay. So yeah, most of what we do these days is online. We try to run everything online. In fact, we desperately try and get everybody to actually sign up online before they come to this event, even though our good friend downstairs, Jaden, is still signing in people today and yesterday. So yes, the Product of the Year nomination forms are all online, and there's a procedure that's set online, and we like to close it off, apparently, a couple of days before this event so they can start reviewing and checking on the process. Sometimes we don't always talk to each other as closely as perhaps we should. Perhaps I should have showed you my slides before. Okay.
Did I look at it?
No, of course not. Yeah, yikes. Okay, all right. So just a word about the papers themselves. Obviously, we want to give a huge shout out. In fact, we're going to give a round of applause to all those people that put a paper in this year. It's very much an integral part of what we do here. We base this whole conference around the technical quality of these papers. For anyone that's been around here a long time, you might remember us as part of the ISA analysis division. And if you remember that well enough, there are papers that run back into the early 50s, 1950s. This conference and part of the legacy of what we do here has been running near on 60, 70 years. So it's a fabulous legacy, and we want to maintain that legacy and look after it. So we build our entire conference around the quality and the hard work and the effort that goes into these papers. So we would encourage everybody to come in here and support them, to listen to them, and to give them all their time and attention and mark their scores at the end of the day there. My one little final note, I always like to give you a little bit of a technology note. And this year it was actually going to be a small time for a keynote speaker. Wes has a friend from church.
You saw a lot of him. He was Mr. Glover, the black man, and he is a man of God, I will tell you. And he will be our keynote speaker next year.
So you're going to get an upgrade, I think is what Wes is saying, next year. You get a NASA astronaut instead of this lowly old Englishman.
We'll see. I have to schedule him because he's going to probably be on a box of weeds or something.
So as it turns out, we were going to have him come here, but he's marginally busy at this time of year right now.
Yeah, off the planet.
So he couldn't make it for whatever reason. That was a little lame, I thought, perhaps. But anyway, so I looked up on NASA, some of the cool things that they do. And I just wanted to put them out there because it's sort of part of, there's a parallel between the incredible space science that they're doing and the kind of lowly science that we do here. And I really like that parallel. So, they know exactly how much hydrogen in the sun. They know that we found helium in the sun before we ever found it on the planet. They know there's this crazy planet that's 700 light years away that has water in its atmosphere. They know there's a galaxy at 150 million degrees of Fahrenheit. They know there's a galaxy moving away from us at 280 miles a second, something I'm not keen on the Earth. We know closer to home what the ozone content is of our own atmosphere and how much it's saving the lily-livered skin of this pale Englishman every day as it blocks out that UV sun for us. Why is that cool? Because it is all spectroscopy, and it's all the stuff that we know. There's this incredible parallel between, we may be one of the very few industries on the planet that can actually understand how some of this stuff works. And to me, that is super, super cool. When we were born off the mothership of laboratory analyzers some 70, 80 years ago, one of the first things we started to do in the process analyzer industry was spectroscopy. And to this very day, it's one of the corners of where we are as an industry. As you listen to the papers in this hall, as you walk around the vendors' hall, you will see so much spectroscopy in action. And I like to think that we are those folks that have some kind of minor parallel with what's going on at NASA and all the super cool things that they're doing down there. So I kind of like that. I think it's cool. I think it's very, very cool. I found this quote from Aldous Huxley. He said, "It's dark because you're trying too hard. Lightly, child, lightly. Learn to do everything lightly." Personally, as a brilliant scientist that he was, and great writer, I like to think he was talking about spectroscopy. But I kind of doubt it. And he did a lot of acid. So, who knows what Aldous was talking about, but I like the quote anyway, so there you go. Thank you for that. We truly hope you have a wonderful week. We hope you catch up with friends. We hope you meet new friends. We hope you learn something in this hall. We hope you see something super cool in the vendors hall. And above all, I think the three of us, for all of the committee, are super happy that you will all come down to Galveston again and spend this week with us. Thank you very much. Just give us 2 minutes and we will set up our first session. I think we're just about on time, right, gentlemen? And we'll get our first speaker up and we'll start the first session here. We're very happy to have our first speaker up. I'm just going to pull up the, I got the title right here. So the title of our first paper is Direct Quantification of Etching Baths Components Using Process Raman Spectroscopy, and it's by the speaker and author here, Elena Hagemann. Just a little bit bio on Elena. She is a seasoned expert in spectroscopy, very topical for my talk, and currently serving as the product manager for process spectroscopy at Memoriam USA. With more than 12 years of specialized experience in near-infrared and Raman spectroscopy, she has built a career dedicated to advancing process analytical technologies across all industries, across many industries. So thank you. Welcome, Elena.
Thank you. Yeah, good morning, everyone. Thank you for your time and attention this morning, and I appreciate very much that Stuart started with spectroscopy and this interesting keynote. I do spectroscopy since 12 years, and I'm very excited to present this application to you. If you heard my presentations before, I present one specific application, the etching bath components by Raman, but I also try to teach a little bit about what's important about spectroscopy, implementation, model development, while I talk about one specific example. I want to set the baseline, talk a little bit about etching bars, the RCA, and what kind of challenges do we run if we want to maintain those baths. Then talk a little bit about vibrational spectroscopy. What challenges do we have if we use NIR spectroscopy for exactly this application, and why do I think we should go towards Raman spectroscopy for this specific application. Talk about the experimental setup, how we quantified some components in this bath, and then talk about implementation and, of course, the conclusion. Shall we go NIR or shall we go Raman with this kind of applications? And then we have a little question and answer session at the end of my talk. So an etching bath, and as I say, this is a semiconductor application, but all of you in all of your industries, you have something that you need to monitor. And in etching bath itself, it is very important that we look into the bath components because we have active chemicals reacting with a surface, and we want to ensure that we have the right concentration of something in this bath, because while it is reacting, chemicals are consumed. We have byproducts that get created. We have contaminants. And in order to have our components the way we want them to be, we need to ensure we have the right concentration in a bath. Some examples, and the example that I'm going to talk about is an alkaline cleaning bath with the APM solution. And now it's the time where you think about your kind of industry. Where are you monitoring things where you need to ensure that you have the right concentration? Because spectroscopy can do so much more than this one application that I'm going to talk about. So the specific application, the RCA cleaning bath, is specific in semiconductor industry, and the reason for this chemical bath or this application is to ensure that we have wafers very clean, very well prepared, and so there are different chemical baths that the component gets exposed to achieve this clean surface. And it's spread into or split into two steps, the SC1 and the SC2 bath, and we are going to look today into the SC1 bath, where we have ammonium peroxide and then hydrogen peroxide in this mixture. And I talk later, this graphic will come back again and talk about the implementation and the challenges that we might have with that. So if I say it is very important that we need to monitor those concentrations in a bath, what kind of challenges are we running usually into it? We can do, and it's, I don't know if I can point at something here. Well, on the right side, if we have offline analysis where we have grabbed samples, expose a human being to taking a sample out of the production, bringing it to an offline lab, we know we don't want to expose our operator, but the biggest challenge there is the delay and the frequency of how often can we actually monitor the concentration in a bath. By the time we get the result back, things have already changed and we maybe have to throw things out, right? That's in general when we monitor something, if there's a delay, we don't really monitor something in real time. We can bring analytical technology closer to where things are happening, but then we still have in an at-line setup, someone needs to bring a sample to the technology and there's some form of operator exposure and delays between analytical result and the actual action. Online instrumentation takes one component out. We don't have an operator bringing samples anymore. The sample is transported to the online technology. So we have faster response and a form of automation. And probably where we want to go at one point is do inline spectroscopy, where we measure exactly where we are interested in seeing those results. We have the automation and the real-time results because it's super quick and we can react right away. And so industry kind of has already shifted towards using spectroscopy for this etching bath monitoring. And that's the main topic of my talk today. What is vibrational spectroscopy? Not all of you have done spectroscopy in the past, and Stuart already said it's the interaction of light with matter. And it doesn't matter if you do NIR or Raman or whatever other vibrational spectroscopy, you have an incident light, a lamp or a laser or something that you shine onto your sample, and then we have some form of an interaction with this light. If it's absorbed, if it's scattered, however it is interacting with this light, as a result, we get a spectrum. And the spectrum itself is not very smart. It cannot do much. It's just a spectrum. But there's a lot of information inside of a spectrum. And we can use this information, for example, for identification, but also quantification. So identification, where do peaks show up in the spectrum, can be assigned to functional groups. For quantification, we look into the intensity of those bands and correlate it or link it to actual reference values. And that's what I said earlier. It's a secondary technology. By linking it to information, we make spectroscopy smart. And so application development, and what I'm going to present is an application feasibility study for one of our big main applications that we are interested in promoting, is you have to scan your samples, you have to have samples spanning the range that you're interested in, get your reference values, apply chemometrics, and some of my chemometrics friends, they will love, but it is nothing more than fancy statistics, right? You bring data, you treat the data, and you get good models out of that. And then once you have the models, you can run spectroscopy, and you do not need to bring samples all the time to your other reference technology anymore. And so as I mentioned earlier, industry for semiconductor and for a lot of other industries have already moved towards using spectroscopy, but there is a challenge with NIR spectroscopy, for example. It's an for samples where you have a lot of water content in it, usually the spectrum is pretty much saturated and people still use this spectrum and do some kind of an indirect correlation to the reference values, even though there's not truly the information in the spectrum. It's saturated, it's overlapping bands, and you don't really see it anymore. It helps us if we want to do very low moisture content. That would be great, right? If water content is low, then we can use NIR spectroscopy, but for a lot of aqueous systems, it's just overlapped. And it's still be used. People still use NIR for etching bath control, but I want to show that an indirect measurement is not truly what we want to do. We want to use specific bands and do a direct approach, and not just by some background shifts or whatnot. And also NIR spectroscopy, if you have water in it, is very temperature dependent. So for the experimental setup, to move this industry standard of using NIR towards Raman spectroscopy, we used a process analyzer, 785 excitation wavelengths. We needed a broader range from 150 to 3350 wave numbers. And of course, for the implementation in process environment, we need everything very ruggedized and customized, because each environment looks different and needs the specific interface to get good spectral data. To show you how fast everything is, the integration time for each sample is about 11 seconds. That means every 11 seconds you would get a new data point of what is actually happening in this bath. And then we prepared the samples, had validation samples, ran through the whole application development. And I want to talk about how the spectra looked like, how we did the model development, and what our conclusion is. So here we are looking at the spectral overlay of this APM etching bath solution. And you might say, well, there's again this detector saturation part of the spectrum cannot be used. But if we look into where those components actually show up, it's at 875 and 3250. Those are the regions where we have very significant peaks representing the components in this etching bath. I zoomed in one of those peaks so that you can see nicely with an increasing concentration. We also have an increase in this specific band representing hydrogen peroxide. And then we used the data, ran them through chemometrics to build those models. And some of you might look at the R square and say 9974, that's not good enough because we want 9999, because that's what we do maybe in chromatography. But for spectroscopy, it's very important to look into how well does this model predict. So our calibration error, cross-validation error, prediction error in comparison to the error of the reference technology. And so looking here at the SEC, SECV, calibration cross-validation error, we are looking at 0.04, 0.05% plus minus as a predictive error in this range, which is good. We can add more data, make it more robust, but it shows definitely the feasibility of this application, and it shows that it's a direct peak that we use and not just some baseline shifts in like other spectroscopy technologies. That was the first approach. And then, of course, we also had some check samples, because once you build a model, you also have to apply it onto samples to see how well does it actually predict, and not only on the samples that you use for model development. And so we used a couple of check samples, ran them 10 times to get our statistics, like the average, standard deviation, repeatability, and all of these kind of things. But again, looking into the predictive error, that is what we are interested in. How well does this model apply when we expose it to new samples? And it falls nicely into the range. It's slightly higher than the calibration and cross-validation error, but that's always to expect when we expose it to something new that it hasn't seen before. We did the same thing for ammonium hydroxide, choose the different band of the spectrum, so narrowed it down. We didn't use the entire spectrum, just the specific region. increased the concentration, got the reference values, built the model. What I forgot to mention earlier, there's always some data pre-treatment involved. So if you have baseline shifts or noise or something, then you pre-treat the data to make it more useful for the model development. And same thing here, looking at how well does this predict if we apply it onto our check samples. That worked very well. That's showing us that Raman spectroscopy is an alternative for etching bath monitoring. And now I want to show you a little bit about how this application would be implemented then into real environment. What I mentioned before is we have this chemical bath, and the chemicals get kind of circulated through this bath. So there's a lot of tubing, there's a lot of pumps, a lot of motion going on. Also, if we have contaminants or byproducts, they would need to be filtered out before it goes back into the chemical bath. So where do we need to measure? It's always past those filters, a little bit away from where pumps and these kind of things are installed, because all of that would have an impact onto the spectrum. We need to make sure that whatever we expose it to doesn't corrode, right? So coated sampling interfaces, coated flow cells is important to have it resistant against those chemicals. And we can either do that with like going through a watch glass, having clamp-on flow cells, or flow cells with a sapphire window to look into where we are actually measuring our sample. Yeah, that brings me to my conclusion. So we can use Raman spectroscopy to monitor etching bath, and it's a direct measurement. It's a good alternative to this indirect NIR spectroscopy, and especially if we have an aqueous environment, water, we don't see it with Raman spectroscopy, and also it is less temperature influenced than NIR would be. Well, that's all that I have for now. If you have some questions, I guess we still have some time.
Yeah, excellent presentation. I did have one question. Toward the end there, you mentioned that you put the sample cell area after the pumps to avoid interferences. I guess I was surprised. I did not expect flow or pressure to have an influence. Did I misunderstand?
So we definitely want to make sure that those pipes are always filled, so you do not measure where gravity, for example, is. We always want it past the pumps, nicely flowing through wherever we are.
So it's more of a laminar flow issue rather than a pressure issue, or something like that.
Yeah.
Okay, that makes more sense.
Anyone else? Anybody else? More questions? Okay, thank you very much, Elena.
Thank you.
Oh.
So for this setup, we had about 20 samples. The implementation will probably take more like 40 or 50 samples, and whatever is happening in your environment will need to be reflected in the samples that you're measuring. If your run, or whatever we are looking at, takes a couple days, then we would want to measure samples throughout those days. If it's a 24-hour exchange, then you collect spectra over those times, but you need to make sure that everything that could happen is represented in that data, and the more complex things are, the longer it takes to capture this variation, if that makes sense. And probably an add-on to that, we have applications that are implemented within a day or two if we did some pre-work, and there are applications that take some weeks or months, depending on how fast do we get the data we need to represent what is happening. But this is easier because we have less components also in the mixture.
Anyone else? Okay, thank you very much.
Thank you.
All right. right, our next speaker is Monique. Monique is also one of our trainers in mass spec, so we're very happy to have her back for a second day. Thank you very much. Utilization of the quadrupole mass spectrometry for analysis of phosgene in ambient air. I have a little bio that I found from yesterday for you, Monique. Monique is the Global Product Manager for the mass spec and the CDRS at Process Insights. She has 8 years of experience with quadrupole mass specs, focusing on operation, maintenance, troubleshooting, applications with previous education and experience in analytical chemistry. We welcome Monique. Thanks.
Alrighty. Good morning, everyone. As Stuart mentioned, we're talking about the utilization of quadrupole mass spectrometry for the analysis of phosgene in ambient air. Now. No worries. Alrighty, back to it. Okay, so we'll talk about a brief introduction for the importance of ambient air monitoring, the history of phosgene, an introduction to quadrupole mass spectrometry, theoretical analysis of phosgene using the quadrupole mass spectrometer technology, as well as some of the field challenges and solutions that we encountered in the implementation of this application. Importance of ambient air monitoring. So we're probably all very familiar with ambient air monitoring. This comes to us from a few different regulations really established in the US in the 1950s and 70s with the Occupational Health and Safety Act, or OSHA, and the Clean Air Act, which were both adopted in and around about 1970. They've had several updates through the years, but the core of the mentality between these two rules and regulations for the US government remain the same to protect both worker safety as well as the ambient environment around us. These two acts created OSHA and the EPA responsible for setting and enforcing these standards relating to protecting workers, the environment, and public health. Under OSHA, they established permissible exposure limits for various chemicals that pose a risk to worker safety. Advancements in technology, experience, and available scientific data, it's been acknowledged that OSHA limits are not adequate to protect workers in the US right now, and it's also part of the government. Things take a really long time to update. So most professional organizations both domestically and internationally, supplement OSHA PELs with more stringent guidelines from Cal-OSHA, NIOS, and ACGIH, which are more common and more stringent than standard OSHA regulations for different chemicals. History of phosgene. So phosgene is a toxic, colorless gas produced by passing chlorine gas through purified carbon monoxide through a bed of activated carbon. It can also be inadvertently generated through combustion, biologically, or through atmospheric chemistry. Approximately 12 million tons of phosgene are produced annually worldwide. Due to the dangers of transportation and how toxic this chemical is, it's often produced and used in the same facility to create polymers, pharmaceuticals, and agrochemicals. Phosgene was first produced in the early 1800s by exposing carbon monoxide and chlorine to sunlight. Industrial synthesis was created in the late 19th century by passing that carbon monoxide and chlorine over that activated carbon or catalyst. Early industrial uses included chloroformates, acid formates, dyes, pharmaceuticals, and agrochemicals, with modern uses focused on the production of isocyanates and carbonates. Phosgene was also widely used in World War I as chemical warfare agent, so therefore it is established not only under OSHA and the EPA as a hazardous air pollutant, but it's also a Schedule III chemical for the Chemical Weapons Convention due to the large-scale industrial uses, but also the extremely well-known viability as a toxic chemical weapon. The regulations for phosgene in terms of Cal-OSHA, OSHA, and NIOSH set the limit at about 100 ppb or 0.1 ppm. The MAX 300 or quadrupole mass spectrometry has a detection limit of 50 ppb or better. Advantages of mass spectrometry. So how does an industrial mass spectrometer work? So this technology takes a constant flow of gas into the analyzer. Each sample is ionized and scanned electronically. Each scan produces a set of peaks specific to the composition of the gas, and all gases can be ionized, measured, and detected with a mass spectrometer. So not only are we talking about hydrocarbons, air components, sulfurs, solvents, really any gas or vapor sample can be analyzed by a mass spectrometer. On the bottom here, we see a mass spectrum or fragmentation pattern for methane. Not only can we identify the bulk molecule of methane, but also the fragmentation pattern as it goes through that ionization process, seeing differences between the molecule at its full form versus fragmented form, as well as understanding isotopes of carbon or hydrogen that could exist in this molecule. And this type of fragmentation pattern exists for all chemicals. Sampling systems for ambient air monitoring with use of a mass spectrometer or any other technology will include end-of-line filters to protect the sample conditioning system, a sample flow rack to ensure a fresh sample, a high-flow sample pump, and then a sample selector. So to ionize the gas and put a positive charge on it, we have a current continuously applied to an active filament to heat it up and emit electrons. The capillary or transfer line will leak a small amount of sample into the ionizer, where it is bombarded by electrons to make positively charged ions. Those positively charged ions are then attracted towards the lens stack where there's a negative voltage, having that positively charged molecule pull out of the ionizer and propelled into the quadrupole mass filter. Ionization happens to all molecules in the gas stream simultaneously before we get to the mass filtering where we actually start to separate and identify different chemicals. Quadrupole mass filters filter by mass. So quadrupole mass filter uses radio frequency and DC voltage applied in a ramping and sinusoidal pattern to create an electric field that filters molecules by their mass. Depending on the amplitude of that RF to DC ratio, it will allow different masses to go through the mass filter at different times. After the mass filter, everything goes to a detector and data processing. So for a dual detector, we need to identify both the large bulk air components as well as the trace chemicals that we're looking for. So we use a dual detector, so that's going to include a Faraday plate. Faraday plates are usually good for single low double-digit ppm values the whole way up to 100%. It's usually a 1-for-1 ion to concentration type of arrangement on the data acquisition and processing versus an electron multiplier, which has a detection limit of single to double-digit ppb and is usually good to about 50 to 100 ppm. These do work in conjunction and can switch from one to another if there's a large release going beyond that. An electron multiplier amplifies the signal, so there's usually somewhere between a 500 and 1,000-fold increase in the signal for those, so you get a very clear signal at very low levels using the electron multiplier versus a 1-to-1 Faraday plate, which is good for high concentrations, but not necessarily low concentrations. All of these happen in a data acquisition software. The Quester 5 software used on our systems is intuitive and flexible, meant for long-term, continuous, 24/7, 365 operation. Some of the advantages of using a mass spectrometer in ambient air analysis is that it really specializes in the measurement of hazardous air pollutants and molecular masses greater than that of air. Not necessarily good for continuous emissions monitoring for your CO, NOx, things like that due to the interference from ambient air. But once we start getting into those hazardous air pollutants and toxic gases, the mass spectrometer exceeds because there's very little interference in the spectrum at those levels. Mass spectrometers are also sensitive, selective, fast, and very flexible. So today we might be looking for Phosgene, and that could change based on looking at different chemicals in the future with the same technology with very little changes. Theoretical analysis of Phosgene. When looking at a mass spectrometer, we go through a theoretical review of the application for this to understand both the masses, the interference, and the response factor of these chemicals, not only our chemicals of interest, but all of the chemicals in the gas stream that we need to monitor to understand interferences between them, as well as any reactions that may need to be there. There's going to be two parts to the theoretical analysis, and that's going to be our fragmentation matrix. So a fragmentation matrix identifies all the components of interest along the left-hand side that we need to look for in a gas stream, as well as the detection masses where we will detect those molecules and understand the interference that one component has on another component in that analysis method. So here we see Phosgene highlighted in red. We're measuring it at mass 63. And in this matrix, we not only are looking at air components, but we have additional contaminants that may interfere with the analysis of Phosgene that need to be taken into consideration. Particularly of interest for this, it would be carbon tetrachloride at a very low 0.3 ratio of intensity, but we have a very clear Phosgene peak at mass 63 for that analysis. The second part of that comes into the stream evaluation. Not only are we looking at what interferes, but then also how clearly we can see the signal from our target molecule versus the independent molecules around this. So this application gives us that we have about a 50 ppb detection limit. We have very low interference from other chemicals, and we have a very low standard deviation for the system, but we would have about a 50 ppb detection limit. Depending on the availability of gases and confirmation of these levels for field use, we will also follow up with testing in-house. In-house testing for this revealed about a 25 ppb detection limit for Phosgene in ambient air, exceeding what our stream evaluation estimated for this performance. Field challenges and solutions. As much as we like to think that everything goes perfectly from our theoretical analysis, we often find when we go to the field that things can be different and not quite what they seem. This particular application yielded different materials and different issues going on over time. The customer reported long clearing delays, long response factors, and a lot of different issues in the installation after about 6 to 8 months. This was an international installation, so we had a few layers of communication between us and our end user. Not saying that there weren't problems to begin with that we could have solved sooner, but we were brought into the discussion after a period of time. So the first was ensuring that the material selection was correct for the application. So we have different common applications that you can use, such as bare stainless steel, coated stainless steel with an inert coating, something like a Silkenart 2000. You can also move towards Dursan or titanium nitride for additional considerations for corrosivity and longevity of the system. This revealed that using a stainless steel system with Phosgene would yield about a 300 ppb detection limit versus using something like Silkenart 2000, going down to about 150 ppb with a portion of that being stainless steel, or using a completely titanium nitride or titanium nitride. And Silkenart 2000 coated system had the best sensitivity and the lowest LDL for the system. Additionally, there were long clearing delays, reporting sometimes 2 to 3 hours, if not days, to get up to a T95 with the actual field installation of this system. It is common practice with mass spectrometers and any ambient air type system to use a low dead volume stream selector for calibration and sample streams to reduce clearing time. In some cases, alternative sampling is used to as a cost savings measure for the total overall project, or due to the limited number of sample and calibration points. In this particular installation, the integration team selected large outer diameter tubing of a 1/4 inch versus standard 16th inch tubing recommendations, and a sample manifold that created long clearing delays and extended calibration times. We estimate that there was about 18 feet of 1/4 inch tubing that was all connected, so a very large manifold that took a very long time to clear out, increasing those clearing times. And the reliability of the calibration due to those responses and not having the full response factor at the time of calibration. We moved to a low dead volume stream selector and removed the sample manifold, so reducing calibration times from 2 hours to less than 5 minutes for a full analytical response. Most common hazardous and toxic chemicals measured by the mass spectrometer, such as benzene, toluene, xylene, vinyl chloride monitor, ATC, have the same response factor in dry, inert gases from a calibration bottle and when exposed to ambient air humid conditions. Due to the reactivity with Phosgene with water, this component has a very different response factor from a calibration gas to exposure to humid ambient gas. We were noticing about a 30% difference in response factor between calibration gas and nitrogen versus calibrating with clean dry air or zero air. So this led to a challenge with calibration, as most common practice is to use a NIST traceable gas cylinder for calibration. By using mass flow controllers and diluting a certified gas cylinder, we were able to reduce the response factor difference and removing that 30% challenge between the humid air and the dry airs, showing exceptional linearity and repeatability. Here are dilution studies from 250 ppb up to 5 ppm, showing an R² of 1 using this factor and reducing that 30% variability between calibration and sample. Ambient air monitoring is important for all of us in our work, both from protecting the environment and the health of our workers and those around us. Mass spectrometry can be a vast, versatile technology, allowing for accurate and sensitive detections for multiple hazardous pollutants in a single analyzer. And with the right sample conditioning and right material selection, can be very viable for the analysis of Phosgene and similar toxic and hazardous pollutants in ambient air. All right.
At the heart of the mass spectrometer, there looks to be some very sensitive components. And I was wondering if you could address the life expectancy of these sensitive components like an ionizer or even a detection cup. And secondly, with other background gases possible within industry, like to other toxic gases or mercaptans, et cetera, can you get these sensitive components made of exotic metals like a Hastelloy if necessary?
Yes, so for the sensitivity of the dynamics, a Faraday plate is a non-consumable item, so those large level components. An electron multiplier does have, it is considered a consumable item due to the amplification of the electrons. Depending on the usage, you can get somewhere between 2 and 4 years out of that piece of equipment by constantly increasing the voltage to maintain that amplification of the signal. So they do have a long lifetime, and it would be considered a consumable part that would be covered during standard preventative maintenance of an analyzer. When we do start to deal with more hazardous or toxic chemicals, it is very common to need to go to Hastelloy or start to employ different coatings such as Dursan to protect the wetted material of those systems. It's mostly going to depend on the concentration as well as the contents of the bulk gas.
Any other questions? Yes, sir.
Well, from my understanding, that mass spec is a very expensive instrument analyzer and can provide very good measurement for that low concentration gas. So can you share with us why this mass spec is selected for this application? Have you compared this technology with other type of analyzers? Thank you.
Yeah, of course. So in the grand scheme of analytics, yes, a mass spectrometer is more expensive than other types of ambient air monitors, such as GCs and electrochemical cells. Some of the advantages of mass spectrometry include being able to do a myriad of sample points, 10, 20, 30, 150 sample points with a single analyzer by having those. So it really comes into play. If you have one sample point, maybe it doesn't make sense, but if you have a large number of sample points, you can really reduce the cost per point by using a mass spectrometer. And by the speed of the technology, having something with that many sample points is viable because we're talking about 2 to 3 seconds per analytical update versus 90 seconds or 3 to 5 minutes, depending on the number of components. So the speed and number of sample points does make it a viable option in some of these ambient air monitoring situations. Single analyzer for a complete plant. What was your second question? Thank you. Okay, I'm sorry.
Any other questions? Oh, lots of questions. Wait a second. Sample volume is another one, right? You only have a tiny sample volume.
Yes, we do take a very small sample volume, and it's continuous, so that also helps with it being very real time with that 2 to 3 seconds of continuous updates.
I'm just curious, you mentioned the calibration is very tricky in terms of the sampling tubing, whether it's Dursan coated, Soco coated, whatever, and the contaminants of the in the sample gas might also react with your analyte. So I'm just curious how this analyzer doing the validation, how the customer is going to validate over time.
Yes, so normal validation for this type of system would be similar to any other gas. We would challenge it with that NIST traceable calibration cylinder, doing a bump test at the sample point, very standard protocol with that. In this case, we do want to make sure that we're following something like using an MFC to dilute it with 0 air to make sure that we're not introducing a response factor issue with that 30% change of calibration versus actual humid response air.
So the customer has to make a calibration manifold with mass flow controller dilution.
The actual system itself can be incorporated with said mass flow controller, so it's once it's turned on, it has an automated system into one of the sample stream selectors on the port.
Rod? No, I was pointing at. Oh, sorry. Somebody else had a question? No? Oh, perfect. Okay, anybody else? Any more questions? All right, thank you, Monique. Thank you so much. Okay, our third speaker for the session, for this first session, is William Girton. William's talk is on 1064 nanometer Raman for low fluorescence analysis of heavy distillate streams. William is the global product specialist at Horiba Process Instruments, where he focuses on the development and optimization of Raman spectroscopy systems for industrial applications. He holds a PhD in chemistry from the University of Rochester and has a background in nanomaterials, optical spectroscopy, and process engineering. His work centers on improving analytical performance in complex environments such as heavy hydrocarbons and energy systems. Outside of work, he enjoys sometimes spending time in nature and exploring the mountains and the deserts of Utah. We welcome William. Thank you.
Thank you. Okay, is there a laser pointer on there by chance? Well, I can just describe it. No worries, thank you. Okay, thank you everyone. As was mentioned, my name is William Gerton. I'm here from Salt Lake City, Utah, to talk to you, to talk to you about some of our advancements in 1064 nanometer Raman. So just a little bit of background on myself. Now I'm giving you 2 bios, but sure, that's fine. I have my PhD in physical chemistry from the University of Rochester, and I worked on some advanced spectroscopic techniques, specifically on material characterization of nanomaterials. I then went on to do a fellowship at the National Lab of the Rockies in Golden, Colorado, where I continued my work on nanomaterials and doing some advanced spectroscopy and characterization of those materials for all sorts of applications in quantum computing and in energy storage and various things like that. And then following that work, I started with Horiba. I moved to Salt Lake City, where I started my role as a global Raman product specialist, and then I kind of transitioned more into an R&D leader and R&D focused role. So just a brief overview of this presentation. I'll give you a quick background, hopefully not too technical, on Raman spectroscopy, as well as our group in Salt Lake City and some of the great work that we've done over the years to develop a Raman system. And then I'll go on to talking about one of the main challenges with Raman spectroscopy, which is fluorescence interference, and why 1064 nanometer Raman can be a really great tool to subvert that challenge. I'll then go on to talking about a different application that we used 1064 nanometer Raman for, which was lighter gas oil samples, kind of to demonstrate the versatility of this tool, not just in a sample set that's very specific. And then I'll talk about the chemometric modeling results that we got as well, and give you some information about how not only can this be used to subvert fluorescence interference, but also it can be used to develop some really nice modeling results as well. So just a brief background on Process Instruments Horiba. We were started in 1994. So at this point, we have over 30 years of Raman experience. We have a fantastic team in Salt Lake City. And we have a really great group of people who are developing this Raman system that is, frankly, a really impressive system in terms of Raman. If any of you are familiar with Raman, it can be extremely challenging to get, high throughput on some of these samples with Raman. And so we developed this system that has allowed us to, garner experience over the years, as well as now we have systems all around the world and are doing some really impressive quantification in all sorts of applications. And so just a very basic, I guess your second dose of Raman background is, Raman is a light scattering technique at its most basic. When you excite various samples, specifically I'm talking about hydrocarbons in this sense, when you excite a hydrocarbon sample with light, basically just shining light on it, different hydrocarbons, different molecules interact in different ways upon excitation with light. And so one process, and I'll talk about a couple other processes that can happen, but one process, the process that we're interested in, is Raman scattering, whereby when a photon interacts with a molecule, that light can either be elastically scattered, meaning it can completely, or it can scatter the light at the exact same wavelength that you excited it with, or it can inelastically scatter that light, whereby when the light interacts with those molecules, it can move in some way, and then that light can be scattered at a different wavelength, either lower or higher energy. And so based on this process, each molecule that you're looking at has a specific and unique spectral fingerprint. And so because of that, because of the fact that each of these different molecules, specifically hydrocarbons, have specific spectral fingerprints, we can use that to not only identify what sample, or I guess what chemicals are in your sample, but also we can use that as a quantitative technique as well. And so as I mentioned, I was going to talk about other processes that can happen. One of the main ones, aside from Raman scattering, is you can have fluorescence in your sample as well. And so not only do these molecules in these heavier refinery fractions, not only do they scatter Raman photons, but primarily, actually, they will absorb and can re-emit photons as well. And so the absorption and re-emission of photons, known as fluorescence, can significantly outcompete the Raman intensity. And so these processes can be upwards of 10 to the third to 10 to the sixth times more intense than your Raman signature. And so that essentially, if you look in the bottom right corner there, essentially completely swamps out all of the Raman signals that you're interested in, which for some of these heavier refinery fractions renders your sample useless in terms of a Raman application. The primary The primary component that is causing this issue is these polycyclic aromatic hydrocarbons. These molecules love to absorb 532 and 785 nanometer light. They love to absorb it, and they love to re-emit it at a significant intensity. And so we're still interested in quantifying and observing those with Raman, but the fluorescence essentially renders them useless for that technique. And just the main process that is causing this is when you have a photon sent into your sample that we have to do Raman scattering, you can excite these electrons from this ground state into this upper excited state, whereby it can relax and cause that fluorescence that's interfering with your signal. So the primary and kind of an interesting workaround to this is by using light of a longer wavelength or of a lower energy. Essentially what this does is you have a lower energy excitation, and so those electrons are unable to surpass that band gap energy, that energetic gap where between the ground state and the excited state is no longer accessible. And so essentially you're blocking out that radiative relaxation pathway that is interfering with your Raman signal. And so in doing this, you're essentially eliminating that absorption and re-emission process, and what you're left with is the peaks of interest that were there all along in the fluorescence samples. They were just invisible due to the fluorescence process. And so just one example, I'll give you several other examples, but just one example of this, as you can see in the blue line there, you have significant fluorescence interference when you use 785 nanometer excitation. All of those peaks that are visible in the orange spectrum, which is used from 1064 excitation, you can see that all those peaks are invisible. And then when you decrease the energy of excitation, you still have the same Raman signature. That's the important part, is you still have the same Raman signature of your molecule, except for now you're not exciting that fluorescence pathway. And so to do this, to modify our instrument in this way, we have had to modify just a few components of our system. The Raman that we're using is still a non-invasive process, but we've had to make some modifications to our system in order to do so. So we've had to change things like gratings, fibers, changing cameras, because different wavelengths of light are going to interact differently with the various components in your system. And so we've developed this new system in order to be able to function properly with near-IR light. So the first example of kind of the efficacy of this 1064 excitation, we looked at an array of heavier gas oil samples that had a varying degree of optical densities. And you can see that upon 785 nanometer excitation, which is our wheelhouse for excitation, and the primary excitation wavelength for most Raman companies as well. You can see that in just the raw data, which is pictured in that middle graph there, you can see that it's essentially swamping out all of the peaks that we're interested in, right? For quantification, for identification of various properties in your sample as well. And then even upon background subtraction and baseline, you can still see that most of our peaks are invisible, and that essentially these samples are just inaccessible with the current configuration. And so without a workaround to this, you probably would just have to give up on these samples in terms of wanting to quantify them. And then you can see that upon analysis of the same sample set with 1064 nanometer Raman, you can see that the property that I was mentioning before really rings true. You can see there's a significant reduction in the fluorescence baseline, as well as new Raman features that are becoming visible, and not only visible, but also highly resolved. And then upon further baseline correction and normalization, we can further enhance this peak definition. And so this really demonstrates that the 1064 nanometer excitation is a really unique workaround and allows you to access samples that were previously inaccessible with the 785 nanometer configuration. And so this is important because it allows us to take some of these peak intensities and integrals and peak positions, and it allows us to go back and do some chemometric modeling so that we can actually use it to quantify properties such as pour point and viscosity, and I'll show some of the modeling data that we've gotten with this as well. And so when you do a side-by-side comparison of the two, you can see that obviously there's a significant enhancement in your signal-to-noise ratio when you quantify it. It's kind of maybe not the most sensible thing to even try to quantify signal-to-noise on the 785 samples, because essentially that background is is essentially all noise, and so you get a significant enhancement in the signal-to-noise ratio comparison, and that's important again for identifying peaks for when you're doing modeling as well. And you also get the appearance of peaks that are completely obstructed in the 785 spectrum around 1100, 1150, and those peaks are important hydrocarbon peaks that we're interested in quantifying. So, and so the next experiment that we ran, that kind of we were trying to build a case for why 1064 is important. Not only can you access samples that are previously inaccessible, we want to make sure and validate that 1064 Raman can be used in applications that 785 is important for as well. And so we shifted just slightly from the heavier, really dense hydrocarbon samples. We shifted a little bit to the left, where 785 is still useful in that regard, but maybe we can see some reduction in that baseline further, and also validate that 1064 can be useful in those applications as well. So we looked at a separate array of lighter diesel fractions that were taken over a 10-day period, and over those 10 days, there's a further reduction in the polycyclic aromatic hydrocarbons that are causing this fluorescence, and so we should be able to see some fluorescence background, but obviously you can see the spectrum here is displaying the 785 nanometer Raman collection, and so it's still viable data, but we want to see, can we get a further enhancement, or can we still see these properties with 1064 nanometer Raman? So again, there's a minimal fluorescence background. You can still see peaks really strongly, but we want to see if we can validate it with 1064. And so when we analyze it using our new Raman configuration, you can see that there's a further reduction in the baseline intensity. There's only about a 20x enhancement in the signal to noise compared to the heavier diesel fraction, or to the heavier gas oil samples. But this essentially is just telling us that, yes, we can access these samples that are also usable in 785, and then we can also do samples that are completely inaccessible with 785 as well. And so it's also compatible with lighter fractions in that way too. And then to move on to just some very basic modeling that we've done with 1065 as well. Sorry, 1064 as well. You can see that we have really nice agreement with our modeling results for chemical properties such as viscosity, and we also have a really low or good agreement with the residual plot as well, which is telling us that our model is agreeing nicely with some of these known metrics, and that it is essentially displaying that 1064 is a viable option in terms of building some of these models. And so that previous slide I was showing is just for the predicted modelability of the 1064 results for viscosity, and then also has a good agreement with pour point as well, with decent R-squareds, and then good agreement in the error variability as well. And so just to kind of wrap up what I've talked about, I think as I mentioned, just 1064 is a really nice alternative for measuring samples that previously with more you know, with our current and most other current Raman applications that use 785, you can now access, you know, a pretty large regime of samples that maybe were invisible before because of this fluorescence interference. And it's not just hydrocarbons, you know, lots of other samples have fluorescence interferences. And truly it comes down to that figure in the top right, where if you're not exciting electrons into that excited state, you're not going to get fluorescence. And so that's the workaround to that too. So yeah, thank you. I appreciate it.
Didn't think about it, sorry. So I understand for samples that really show high fluorescence, the 1064 is definitely beneficial, but the application that you just presented where 785 would give us some results.
Right.
So what's then the downside in the implementation? If 785 would be an option, but you choose 1064, so is there any downside when it comes to the actual implementation?
Right, sure, of course. And I think you being the Raman expert probably know what the answer to that is that, you know, the longer wavelengths of light have, you know, a significantly lower proportion of scattered photons in Raman. And so the reason we want to demonstrate that applicability is because, as I mentioned, the different wavelengths of light interact differently with your components in your instrument. And so you can't use a 1064 excitation in your 785 system. So you have to have a completely new grating and lens and camera in order to do that. So you can't just switch out a laser. Unfortunately, it's not that simple. As I'm sure we all know, CCD cameras have different degrees of quantum efficiencies over different ranges, and so you can't, unfortunately, just switch out the laser. And so, but yeah, the main issue with applying 1064 to the regime of samples where it is accessible 785 is the scattering efficiency is much lower for 1064 than it is for 785. So for, you know, every one scattered 785 photon, you probably get like maybe 0.2 scattered photons from 1064. And it depends on the sample as well too, but it's primarily due to the fundamental fact that higher or longer wavelengths have a lower scattering potential than they do for shorter wavelengths. So, but again, well, I can't go back. But again, the main problem with the fluorescence is the higher energy has a higher scattering potential, but it fluoresces. So it's kind of a balance. You have to really assess what's important for your system. If your system is really obscured by fluorescence, then you don't really care as much if it takes, you know, maybe 4 times as long to acquire those samples, because even if you looked for 20 minutes with your 785, you'd never see those samples. But if you look for 20 minutes with 1064, you'll be able to see those samples. So.
Yeah, I definitely agree. I definitely agree that for certain applications you can do that with 785. Just for practicability, you have to use longer integration times. And I was just thinking, when our folks that use process implementations, if they want to implement it into their productions, then there are some downsides that would come with 1064, and that it's very valuable to make the right decision for the final implementation. Then.
Exactly. Yeah, and that's a great point. It's really you have to dive deep into your specific analysis. Like what are you focusing on? Because we have a lot of customers, and we know a lot of people who, you know, they have a huge sample set that with their Raman configuration is completely inaccessible. They can't look at it. So oftentimes it just gets kind of tossed out, even though they do have interest in quantifying, you know, or wanting to know what's in your heavy gas oil samples, or also, you know, wanting to know the physical properties like pour point and things like that. You can't measure it because it's, you know, you're going to see fluorescence obstruction. And one thing I didn't put in here that, you know, we've looked at really low laser powers, maybe decreasing the power and increasing your acquisition time could potentially eliminate that fluorescence background as well. But even if you have like a, you know, 50-minute exposure and like a, you know, a 1 watt laser, a 1 watt, or sorry, not 1 watt, a 1 milliwatt 785 laser, you still see a significant obstruction because, you know, fundamentally that energy is high enough to make it fluoresce. So, yeah.
Any other questions? Yes, sir.
And we're just wondering, so have you any experience and apply this where you utilize this technology in bioprocess industry, like, measure the concentration of ethanol and acetic acid concentration inside of that fermentation broth? Because we have bacteria, what kind of chemical inside, how successfully this technology can be used for inline measurement. Thanks.
Well, we haven't measured samples like that specifically because I don't really know what the fluorescence profile of those samples would look like. So again, if fluorescence was an issue in those samples, I think we would be able to measure them. But these samples, as I mentioned at the beginning, are really prone to fluorescence because of those polycyclic aromatics, right? The ones that have lots of rings on them. They love to absorb and fluoresce. And if you have a sample that has a large quantity of those, some biological samples do. And so, yeah, in those samples, absolutely, it's the same process. If you're not able to succeed that energy band gap, then you can eliminate that fluorescence. And so it is also a tricky balance too, because you're kind of in this like weird regime where maybe your sample looks kind of crappy, and you're like, oh, it's just fluorescence, and so I'll just excite it with lower energy, and it still looks like shit because maybe it is, because if you're going to look at a sample that maybe isn't very good to begin with, it could also be just a truly large background. Some of these samples are vastly complex matrices. You have a lot of stuff in there, and so when you look at them, it looks like a lot of stuff. There's tons of peak overlap, and so it's even if you're eliminating all the fluorescence and you're looking for a really long time and you have a really sensitive instrument, you're still looking at a sample that is not necessarily visible. So, yeah.
Any more questions? Okay, thank you, William. Thank you so much.